Welcome back to the next installment of From Atoms to Axons with
Ibrahim Shahrur
and Bilal Hamoud. On today's docket, we're going to be discussing an interesting topic. Abe, are you familiar with entropy?
Oh, yes, I am.
Are you familiar with what a perm is?
A perm?
A perm.
What's a perm?
It's a style of, it's a type of hairstyle you can get after going some intense heat and a lot of chemicals on your hair. It kind of gets this nice frizz thing going, like an 80s theme, something in the past. Now imagine that frizzy, wild hairstyle as what entropy is.
Huh. So that's what entropy is.
Yes, frizzy hairstyles that moms have from the 80s.
I wish my professor was so clear about it, because now it makes perfect sense.
I'm glad you understand. But for today's topic, we will be discussing entropy, which is a physics phenomenon. Abe, would you like to describe its actual definition?
For sure. Just to be clear, we're going to talk about entropy and how it's related to many other things. So how entropy is related to life, how entropy is related to engines, and how entropy is related to time. So today is going to be really fun and really interesting. So stay tuned. If we want to start off with like a definition of what entropy is, I'd rather keep it to the end so that we have sort of some intuition to what entropy is. Then we can give a definition. But in general terms, when people talk about entropy, they usually refer to some sort of disordered system. You know, if you walk into someone's room and the clothes are everywhere and the bed sheets are not made, they say, oh, this room has a lot of entropy. Technically, that's not the right usage of the word entropy. So hopefully it will be clear.
Are you calling me out, Abe?
Maybe.
I feel like this is a personal attack.
We were just at your apartment, so I don't know.
I don't appreciate this this slander. I'm going to have to denounce those statements. I'm going to say entropy could be more described as, imagine wearing the same shirt for the same days every single week. And it's only two shirts that you alternate between. And you finally expand your collection so that the choices you make for what you decide become more entropic. That is what entropy is like.
I love that description.
No problem.
It's almost
buddy.
like like an example from real life.
Almost.
But so to dive into entropy, I think we should go back all the way to the 19th century.
Wow, that's pretty far back.
That's pretty far back. So there were these two scientists by the name of Lord Kelvin, he's very familiar and popular in scientific circles. If you've ever used the Kelvin scale, if you've ever heard of absolute zero temperature, the namesake is Lord Kelvin. And the other scientist was Clausius. And these two scientists were at the era of engines, and they were trying to figure out how can you make the most efficient engine. Mm-hmm. And so they made the statement about entropy. Each one of them made a different statement. So Clausius' statement was basically boiled down to heat transfers from hot objects to cold objects. And then Lord Kelvin's statement about entropy was that whenever you have an engine that's doing some work, it always has to dissipate some energy into the surroundings. You cannot convert with 100% efficiency the heat you put into work. And so these two statements were basically the starting point of what entropy is. And then at later times, it was figured out that these two statements are actually equivalent. You cannot have one without the other. They're both the same statement. And that was pretty interesting. That was like the start of entropy.
Abe, are you telling me we're talking about thermodynamics? Because this sounds an awful lot like thermodynamics.
Well, thermodynamics is the birthplace for entropy.
Huh.
Then once we talk about Kelvin and Clausius's definitions of entropy, and as I mentioned, they turned out to be they turned out to be exactly the same statement. It was still sort of a mystery, because entropy was this phenomenon that was observed basically in big systems with a large number of molecules. But the thing is, Kelvin and Clausius had no idea that atoms existed.
So they just came up with these theories before the basics of physics was even discovered?
Exactly. They sort of observed these things. They generalized. They made definitions of entropy. They wrote down equations, but they did not know that atoms existed. And this led to many other paradoxes.
That's ridiculous. That's like trying to discuss neuroscience, physics, and philosophy in the same time without knowing that atoms to axons exist.
I know, right?
That's not possible.
People need to
It feels
tune
not
in more.
possible. Right, that's what I'm talking about. Shout out to our listeners. Passive-aggressive shout-outs to our not listeners.
By the way, you could, as always, send us your questions, your comments, and we will respond to you in the Q&A.
Yeah, we'll probably be doing that after the halftime. So we look forward to hearing from you guys.
So back to Kelvin and Clausius, that was sort of the birthplace of what entropy was. They did not have a very clear understanding of what it is at the microscopic level. And in fact, it turns out that entropy is a macroscopic phenomenon. Now, I want to dive into the distinction between microscopic and macroscopic phenomenon. And
Big and little, right?
Big and little, exactly. The big stuff from like a coarse-grained view, from the top view, and then the sort of the atomic view, if you may.
Mm-hmm.
So going to talking about the macroscopic, that's how actually entropy is defined, is that it's a macroscopic variable. And so what does that mean? If you've ever heard of the term exists for the whole but not for the parts, entropy fits that variable, fits that observable. And you could give a lot of examples of things that exist for the whole but not for the parts. For example, temperature would exist for, say, a cup of water, but each molecule of water does not have a specific temperature. So we say that temperature is an emergent property of water. It exists for the cup as a whole, but it does not exist for each atom by itself. And so the same thing could be applied for entropy. It's a macroscopic phenomenon. It only appears once you have a bunch of, in this case, molecules interacting together.
That's very interesting. You know, it's interesting that you say that because the way that the brain interprets entropy, there's an actual article by this really cool group that discusses the theory of conscious states informed by neuroimaging research with psychedelic drugs. So I'm just going to give you the gist of this. They take psychedelic drugs and look at the brain while it's under these, drugs, and it's crazy to see how different parts of the brain light up, and they're relating it to entropy and how kind of these wild firings, these what you'd expect of a brain firings are going off, and it shows these really cool photos of, different parts of the brain that never tend to light up together being active, and it goes into detail of how entropy is involved in this and how they refer to it as an entropic brain. So maybe
an entropic brain.
An entropic brain.
Interesting.
Sounds like me on finals week. But it would be interesting to look further into this. We'll take some of those questions if you guys have them about that. But we're going to move on right now. Abe, did you want to talk about chaos? Because a lot of the times people tend to relate chaos and entropy with one another. Would you say that's true?
There is some merit to that. And in fact, the other day I was at IHOP and I was drinking some coffee, and then, I like to put cream in my coffee.
Uh-huh.
And so as I was pouring the cream in my coffee...
Whoa, I know where you're going with this.
Where was I going?
So you take the coffee
Mm-hmm.
and you take the cream. You put them together. You get creamed coffee. Right?
Exactly.
But beyond this, it's the properties of the cream itself being distributed to the rest of the coffee that represents what entropy is.
Exactly.
And although, like a toddler throwing a tantrum, it gets worse and worse, or I guess more and more erratic with time, it's not necessarily a bad thing that entropy is, quote-unquote, chaotic. Technically, there is no property in physics that says you can't unmix your coffee.
Right, exactly.
So for
there's
Starbucks,
no law of physics that says the coffee cannot be unmixed.
Right. So if the Starbucks baristo messes up your drink and they want to get you a new one, tell them, no, I want this one. Take it out. And, technically it's possible, but...
So why doesn't it happen then?
It is extremely, and Abe, I can't begin to stress how extremely this extreme means. Extremely rare for any sort of reverse entropy process to occur, because imagine every single molecule, every single one has to be able to completely shift out from the other mixed in molecules of the coffee. And it's never, I would be willing to wager it's never happened in the human history and will never happen, but it technically doesn't defy any laws and could be possible.
I'm glad you brought up that example of entropy, because if we go back to Clausius and Kelvin, they had no idea that atoms existed. So then they couldn't explain entropy in that way. But then when we discovered the existence of atoms, then Boltzmann came along, and then he gave a very precise definition of what entropy is. It's exactly how he described it. So let's say we have our cream and coffee, and you first pour the cream on top of the coffee.
And what if I take my coffee black?
Then the entropy of the system would be very low compared to the cream coffee.
Okay.
Yes. But if you pour the cream on top of the coffee, at first, all the cream is sort of bunched up together. It still hasn't mixed up with the coffee, and all the coffee is bunched up together, right? So how many ways could you have these atoms rearranged such that if you look at it from a human perspective, it looks very unmixed, like the coffee is together and the cream is together? There's pretty much...
6 at least.
At least 6, I would say, yeah. Maybe
7?
Maybe 7.
How many episodes do we have? So at least 4.
Yeah.
Maybe 7.
But the number of ways that you could have the coffee molecules separated from the cream molecules is some number, but it's not that huge compared to the number of ways you could actually mix the cream and coffee molecules to have them in the mixed state. So when it comes down to it, entropy really is a statistical phenomenon. It's not some sort of fundamental law of the universe more than it is a statistical thing. There are many more extremely, and I can't stress this enough, like you said, there are so many more ways that the coffee molecules and the cream molecules could be in a mixed state than there are ways that they could be in the unmixed state.
So would that mean, based on the way that entropy interacts with the universe, if I were to flip a coin, heads and tails, is it technically not 50-50? Is there a small, no matter how small, a small chance that it's favored to one side or the other because of the way entropy interacts upon it?
If we take the example of just coins flipping around, then entropy cannot exactly go into a one molecule system or a one object system.
It's just a general thing that's existing constantly.
Right, it's a macroscopic phenomenon, so you need to have a system of many things interacting. Then you could start talking about ways which the system could be some states. For example, cream and coffee. You have so many molecules, so it's only when you have these many molecules that you could start talking about entropy.
So it's a principle of the way our universe works, but not necessarily a physical, there's no physical manifestation that we can directly observe.
You could observe the increase of entropy, and we always do, in fact. If you've ever broken an egg and tried to unbreak the egg.
Oh, man, too many times. Humpty Dumpty, man.
Yeah, good luck with that.
He's not coming back.
It's interesting to ask why that doesn't happen. If you've ever seen those videos of someone diving in a pool and then they're played backwards, you immediately know that video is played backwards. If you've ever seen a car come to rest when someone's braking and then you see the video played backwards, you suddenly see the car start moving backwards. There's nothing in the laws of physics that prevents that from happening. Yet, it never happens.
Well, I have a reverse on my gear shift, so...
That's true, but have you ever seen the floor itself push you?
No, but isn't it always pushing me based on Newton's law?
Good point. But has it ever accelerated you backwards? And so this goes back to the same...
I have a treadmill at home.
How does the treadmill work? You need to provide it with some outside work, outside energy. right?
I just plug it in the wall, man. I don't know.
Exactly.
Stop asking all these questions. Leave that for the audience.
Don't forget to send us the questions. But the reason is when you're watching these videos played backwards, you immediately know that they're played backwards, and it's because these things never happen in real life. They are it's so unlikely for all the molecules in the pool to just gather around next to your body to go in the same direction as to push you up.
Well, you're
And
telling me there's an actual chance that could happen?
there is a chance that could happen.
But
But
isn't gravity a thing?
gravity.
Doesn't that prevent that from happening?
Well, no. If it's the same way, if you play the movie backwards, you give the water molecules a lot of energy. So if you play the movie backwards, that energy that you gave the water molecules, your potential energy from standing up, on the diving.
So it'd be kind of like a trampoline type of thing where you dive in and then quickly get pushed back with
Exactly.
the same exact amount of energy to the same position
Exactly.
with the same air molecules, same everything.
Right. That energy that you're storing in the trampoline is in the elasticity of the trampoline, and then so you're basically stretching it, and then the trampoline wants to go back to its natural position, and so you exchange energy with the trampoline. But if you've ever tried to unbreak an egg, you'll find that it's almost impossible because there are so many ways that the egg could be broken, but only perhaps one way that the egg could be unbroken.
So you're telling me we can't unbreak eggs? So we might as well use them to make a cake, right?
We should use them to make cakes. Cakes are nice. They're tasty.
Right, you
delicious.
mix some batter together, toss them in the oven. There's nothing scientific or anything I have to worry about that, right?
Right. Yes.
Okay.
Then what happens?
Why are you looking at me like that? I feel like I'm wrong here.
No.
Well,
I'm just thinking about cake.
if I know cake, and I know cake, especially tres leche cake, let me tell you, that's my jam. But if I know cake goes in the oven, it cooks, does whatever it does in the oven, and comes out good as new. Well, good to eat.
Good as baked.
And I know that you can't put it back in and put it on a cold scale and uncook those ingredients. You can't unbake a cake. You can't unfry an egg. You can't unscramble
Coffee and cream.
all that, and you can't unscramble the protons. You can't unscramble the
proteins between the
exactly the proteins in the egg. You can cook them and unscramble them, but once they reform as a solid, you can't put them back where they came from. It's like breaking an egg on a microscopic scale, and then you add 100,000, 100 million different scenarios where that's happening. So you can't uncook an egg, and that same principle applies to cake. You cannot uncook the cake because at that point you have broken down these proteins of the eggs, the batter, everything, and then they've reformed in this new delicious, absolutely delicious form. So, Abe, why does this occur?
Now, we should be cautious about saying that these things cannot happen. When we say that, we mean that they can't spontaneously happen. If we just wait and watch the universe unfold, we know that those will never happen. But it's interesting because scientists have actually uncooked an egg, if I remember correctly.
Oh, wait, you're right. They put it in this machine that spins it very, very fast. It's similar to the ones they have in labs to constantly shake a solution.
Like a centrifuge or something.
Exactly that. And I'm not sure how they did it, but they were able to put the eggs in its original position. Now, granted, it's not going to look like an egg.
Right.
It's not going to have the original properties, but the proteins themselves will go back to their original form. And it is absolutely fascinating because you think, this pile of mush here, what's the difference? It's a pile of mush now. But no, it's an uncooked pile of mush, and that has all the difference.
So you might be wondering, well, isn't this an example of this irreversible process being reversed? But the difference is, when you want to uncook an egg like these scientists, you must put in work into the system.
A lot more work.
A lot more work. And then once you do that, it turns out that you actually increase the entropy of the system as a whole. So, right, if you're using some tools, if you're using...
What system as a whole?
So you could include the centrifuge, for example, that you're using, because that needs some energy to rotate and do its job.
The man hours or woman hours that go into it.
Exactly. So you need food to have the energy to do stuff. And
Just eat the cake. Oh wait, no, you uncooked it.
but exactly that. These processes don't happen spontaneously backwards, and the reason is, once again, it's a statistical phenomenon. There are many more ways. Many more ways.
Many more ways.
I missed a many there.
You did. You missed one.
That these things could be in their mixed up, chaotic states as opposed to their very ordered states. Now, whenever we bring up entropy, I would like to just mention why a lot of people don't like the second law of thermodynamics.
Well, what is the second law of thermodynamics? Please.
Right. So the second law of thermodynamics says that the entropy of a closed system must always increase, or at least it never goes down. It either stays the same or it goes up.
Now, closed system. How can you track that?
So a closed system is usually defined as the system that cannot exchange energy with its surroundings, and it's basically closed from its surroundings. It cannot exchange particles. It cannot exchange energy. So, for example, if we look at the Earth, then the Earth is not a closed system, right? But if you look at the universe as a whole, then many scientists do believe that the universe as a whole is a closed system. Now, so restating the second law, it states that the entropy of a closed system must never go down. It either goes up or it stays the same. So that's the second law. And why do people, well, some people don't like it because they're always looking to make these perpetual motion machines. And we've heard about perpetual motion machines.
Abe, let me tell you, I've got this great idea. You put a magnet. Hear me out. You put a magnet in front of your car, right? Really strong magnet, and attach it by a string. And it pulls your car. No fuel needed. You're done. Like, boom.
Exactly. Second law disproven.
Like Tesla, out of business. Ford, out of business.
I wonder why they haven't thought of that.
Bunch of dummies.
Right.
Well, not Elon Musk, never mind. May he rest in, well, he's still chilling. He's doing his own thing now.
He's chilling. Tesla's doing some great things with SpaceX, and I think...
Wait, SpaceX?
Yeah.
I always thought of space eggs. That's why you brought up this whole topic of eggs.
Oh, yeah. That's why the entropy of space eggs always increases.
And that's why the entropy of Elon Musk tends to increase. As you can see, with time, he's just getting wilder and wilder.
That all makes sense.
We should have red flag when we saw the, flamethrowers, but no. Then he shot a car in space. We're like, no, he's fine. And then he got on Twitter, and that's when the needle broke the camel's back. So, Abe, continue with this thermodynamics law that you were talking about.
So I was mentioning the second law of thermodynamics because of these people who want to make perpetual motion machines. And the thing is, the second law is like, a stop sign for all these attempts. It just prevents it completely from happening. Because to have a perpetual motion machine, it means the energy of the system is basically being used over and over again without any loss, without any dissipation to the surroundings. Now, if you remember Kelvin's statement, we know that that is impossible. And a different way of formulating entropy that I think is much more useful to talk about, because sometimes if we talk about entropy as the increase in disorder, we might miss some things. But if we talk about entropy as the dispersal of energy, as in, so for example, the sun has a lot of energy packed into it. And so we say the energy of the sun is a very low entropy energy. However, when we get the energy from the sun in forms of visible light and UV light, and then plants use it and animals use it, then we give off almost exactly the same amount of energy back into the atmosphere and to outer space. So really all the energy that comes from the sun is radiated back. So you might be wondering, well, then how are we using this energy?
It's just being transferred into a different form?
Exactly. It's all going back out as infrared energy. And if we know that
That's right. Because infrared energy is kind of like a heat index. It's because it tracks the amount of heat or energy that's leaving a system, which is why if you're very warm on a infrared like camera, you
yep.
show up very red, and if you're cold, you're very blue.
Exactly. It turns out that infrared light actually has a lot more entropy than UV or visible light, and therefore, when all the energy comes from the sun and we radiate it back, what we're really doing is we're converting this very ordered, very packed together energy into this very dispersed, spread out energy in terms of infrared.
Mm-hmm.
So that's how we are using the energy of the sun.
So you're saying humans are like a... Now, are we spreading out the entropy, which means it's becoming more entropic, or is it more organized because it's in one closed system?
That's a good question. When we talk about life, we know that life is pretty well ordered, right? If I look at...
don't look at my life, but sure.
If we talk about biological life, then that's basically how Schrodinger used to look at life.
I thought he just put cats in boxes.
That was another thing about Schrodinger and his famous paradox, which is actually quite misunderstood in the popular culture. But we'll get to that after talking about Schrodinger's paradox, which is very interesting because Schrodinger, besides being the famous quantum physicist that he was actually thinking about life. And when he was thinking about life, as we all do, he was trying to figure out, well, okay, look, life is pretty well ordered. I mean, the whole point of biological organisms is to take in this energy from outside and to, make up new molecules, to put your organs into a steady system, to reach homeostasis. You're basically reaching a very ordered state in your body. And that's how Schrodinger viewed life. It's a very well-ordered system, right? But then the paradox arose when he started thinking about, well, okay, I know this second law of thermodynamics says that, entropy should always increase, but here we have these biological organisms which have very low entropy, and they seem to maintain this low entropy. And so how does that happen? That was the paradox.
Well, how does it happen?
If we look at the definition, or at least the statement of the second law, and we examine it clearly, there's a key word in there. And that key word is closed. Do you remember the definition of what a closed system is?
One that's not open?
Exactly. Bingo. So a closed system is a system that cannot exchange energy with its surroundings or particles.
So wouldn't that say that there is no closed system besides the universe itself?
That's the key observation. When we're talking about Earth, we cannot look at Earth by itself and forget everything around it. In fact, the sun is right there. And it's because of the sun that we get all the energy, or the ordered energy from, and then we could convert this useful energy to make these ordered systems, life, and so that we could increase the entropy overall in someplace else. So while entropy is going down in our bodies, it is increasing in total at some other place.
So you're saying the only entropy we look at that's constantly increasing is the universe itself. And so although in a individual case-by-case entropy might be going down, overall in the universe entropy is constantly going up.
Exactly.
So if entropy everywhere is always going up, is the universe ever going to reach a point where it's like maximum entropy and it's actually an issue?
That's a great question, because that brings us to the idea of the heat death of the universe.
Inevitable heat death, please.
Well, if we want to talk about different types of...
I don't know what you think you're doing in your bunker that's 10 feet below the ground, but I promise you that's not going to stop the inevitable heat death of the universe.
I wish we could talk about the different theories of how the universe might end, but one of the most interesting is the heat death of the universe. And would you care to tell us about the heat death of the universe?
So in about 4-ish billion years, we know our sun's going to like explode. It's pretty much done. It's going to be like, hey guys, we've had a good run. I'm peacing out, and it's going to collapse in on itself because it's run out of energy. So the universe without humans follows suit because we are the only thing that matter.
That's it. The
that's
universe is death.
So what is the heat death just applicable to all stars?
Yeah, so if you look at the total energy content in the universe, so we know that there are places where they have this very well-ordered energy in them, like the sun, for example, and we have places that are pretty cold that don't have a lot of energy, like Pluto, for example.
Whoa. You mean the 9th planet of our solar system?
Pluto is not a
Pluto is
not
a planet. Abe. You know what? We have a list here on From Atoms to Axons of topics we don't discuss. One of them, a big one, is morality. The second one is if the moon is real. And the third one is if Pluto's a planet. So we're just going to hop off that topic real quick. So use a different planet. Use any other planet.
Any other planet that's really cold. And the idea is when all the sun gives off its energy, it comes to equilibrium with other things. So let me give you a quick example. If you have your hot coffee in the morning and you want to drink it, and then you sort of wait for 20 minutes, you get distracted by a homework problem or something, then you notice that your coffee has reached room temperature. And what that means is that it just basically equilibrated with the temperature of the room. So everything tends to equilibrium. If you have a hot object touching a cold object, then the heat flows from hot to cold, and then they reach a state where they both have the same temperature, then nothing happens afterwards. So now if you think about the whole universe, that's exactly what's going to happen. So objects with higher temperature are going,
Are they going to outweigh the... But isn't space technically cold?
It is very cold.
So wouldn't it, since space is infinite in a sense, wouldn't that outweigh, at least temperature-wise, the heat that could come from any sort of collapsing sun eventually?
But then all that heat that's stored in the sun will be distributed to the surroundings, and then that heat would be distributed to the surrounding until all the temperatures are the same. And so, for example, right now, the temperature of empty space is about 2.7 Kelvin or something. Not empty space, just random patch of space. It's about 2.7 Kelvin.
It's chilling.
It's chilling, yeah. And then if you consider just the universe evolving in, say, 100 trillion years, then pretty much every object with a lot of energy and a lot of temperature, like the sun, would reach the same temperature as this patch of space, 2.7 Kelvin.
Oh, so like how long it takes for my pool to finally heat up, it'll take a while, but it'll eventually happen where all the temperature is about the same.
Exactly, which is going to be a very low temperature. And once you reach that state where every single object in the universe has the same temperature, then you cannot do any useful work. You cannot make a machine run. You cannot generate life.
But wouldn't entropy say that you could?
No, because then that would be the state of maximum entropy.
There's a state of maximum entropy?
Yes.
You didn't tell me that.
That's how we define equilibrium. Is funny because that's exactly when entropy is maximum. It's when all the temperatures are the same, right? And so there is no preferred set of molecules that could transfer their energy into something else. So if everything has the same temperature, then pretty much nothing could happen after that.
So we've talked about the maximum possible entropy. So we know at the very end of our universe, everything's going to be chilling. It's going to be at the same temperature. The whole universe is going to average out.
It'll basically die by heat death.
So what you're saying is because entropy is always growing, when we reach the end of time, we reach the end of the universe. So what if we go back? Does that necessarily mean that as we go back, we decrease entropy? And speaking of coming back, we will be back with you guys after this short break. Come back with us at 6:10, and we will be continuing our talk on time and entropy. We look forward to hearing your questions, and have a beautiful break.
And we're back.
Welcome to the continuation of From Atoms to Axons with
Ibrahim Shahrur.
And Bilal Hamoud. Ladies and gentlemen, I'd like to take a moment out of your time to let you know about Safe Walks. Safe Walks are one of the programs that Wayne State offers its students. It's an amazing opportunity that, and I guess I shouldn't say opportunity, it's an amazing program that they use to help out any student feels uncomfortable at night walking to their car. If ever your life gets too entropic and you are fearful, please don't hesitate to call. Wayne State has a non-emergency number, so it's not a bother in the slightest. They will come, they will walk with you, they will make sure you are safe and make sure you get to where you need to go. Once again, Safe Walks is the name of the program. Call any time at 313-577-6057 and they will direct you to the right place. Please don't hesitate to use that program. I know I have, and it has helped so many people I know. So back on to our topic for the day.
Can you remind us, Bilal, what was the question you asked before we took the intermission?
I think it had to do with time and its relation to entropy, but not just going forward to the maximum amount of entropy, but going back.
So now we're going to tackle the relation between entropy and time as we go back and back towards the Big Bang. Now, you made a great observation. You said, well, look, the entropy of the universe is increasing as we're moving forward with time.
Because if the universe is a closed system, naturally, that means, according to the second law of thermodynamics, the entropy should increase.
Right. So what if we played the movie backwards? Then
the movie of life?
The movie of the universe.
What about the game of life? Can you like
John
go backwards?
Conway's Game of Life?
The one that tends to end with me flipping the board game over and yelling.
You could play that backwards too.
Cool.
Yeah.
It's not as fun.
So the entropy would go down.
Mm-hmm.
And then you keep going back and back until you hit the Big Bang, where the entropy was a minimum.
Minimum, does that mean zero?
Not necessarily. We don't know exactly what the entropy was at the Big Bang, but we know that it was very low. And the condition at the Big Bang for entropy is extremely important for the later development of galaxies and then planets and solar systems and then life. Because without that initial entropy condition, if the universe started out at a very high entropy state, then you would not be able to have all these processes like galaxy formation and solar system formation, stars, planets, and then life. So that's an example of how the entropy parameter of the universe is a so-called fine-tuned parameter. And that's a mystery in physics. Why is the early universe entropy so fine-tuned for life? Now, on a different note, imagine, Bilal, what you were going to say?
I'm just curious. Theoretically speaking, of course, as most of this is theoretical physics, if we were to have a coffee cup present at the beginning of the universe, what would the entropy of that system be like? Would it be an entropic system within the universe, or would it have less entropy to it because of the time at which it was present?
So the way that we measure or calculate entropy is by counting how many configuration of these coffee molecules correspond to the same sort of macroscopic view of the coffee cup. And so I don't think it would change where you put the coffee cup exactly in time. However, if you take the whole system together and move it backwards in time, then the entropy would be going down.
I see. So, one more theoretical question. In the case of Benjamin Button, does his entropy go up or down as he ages?
It goes down.
Okay, so
Yeah.
he's a special case.
Yes.
Got it.
As always, there are special cases to the laws of the universe.
Yeah? I'm just going to float away one day? It's like, oh, special case. Gravity stopped working.
Special case. I was talking about I was going to imagine something. But yeah, imagine yourself in the deep, deep space
Dead.
where there's...
I'm dead.
This
New
is a thought experiment. So imagine yourself in deep, deep space with an astronaut suit, with food.
Sweet. What kind of food?
Your favorite food.
Pineapples and
Pineapples.
pizza. Sweet.
Not together, though.
No, definitely together. That topic number 4, ladies and gentlemen. Do not talk. Let's
Do not talk.
continue.
Imagine there's nothing surrounding you, and then you are asked to point in the up direction. Well, if you look around, there's nothing to guide you, right?
Well,
So
I would just point in the direction of up dog. Are you familiar with that direction, Abe?
I'm not really.
You're not familiar with what?
What's up, dog?
He said it. Oh, dang. I mean, not much. What's up with you? Dang.
The direction of time. That's what's up. But before we talk about the direction of time, let's talk about the direction of space. Because usually we talk about time and space as being sort of different sides of the same coin. If we go back to our thought experiment, there is no preferred direction if you're out in deep space, because any direction is the same as any other direction. There is no preferred direction to say that's forward, that's backward, that's left, that's right. It's just pretty much arbitrary.
So it's based off of a point of reference.
Exactly. If with space, there is no preferred direction of space, so to speak.
So did the Big Bang, if and when it occurred, would it have exploded in a horizontal fashion or in a 360 explosion?
Well, with the Big Bang, it was space itself that was expanding. And when you talk about space itself expanding, you're having more and more space, more and more three-dimensional space. But there is still no preferred directionality of space. There is no, or that's forward. There's no big sign, cosmic sign up there that you could look at night and say, oh,
This way up.
this way up, exactly.
Oh, Mom, there's Mars. Oh, there's Jupiter. Oh, there's the this way up sign.
Exactly. And
Okay.
then, but the difference with time is that there is quite obviously a direction to time. The past has already happened. The future is yet to come. We remember the past. We don't remember the future.
Unless you're psychic or in the 4th dimension.
Which is
Well,
time.
the 4th dimension is time.
So since we are in time and we're moving forward in time, and we know that time has a direction as opposed to space, and so this question was troubling physicists, and it still is. It's still a very hot topic. But there is a potential solution. And if you've been listening along, you probably know what that solution is. Entropy. The second law of thermodynamics
Is the solution?
could be the solution, yes, to the arrow of time, to why time moves from past to future as opposed to like space, which does not have a direction. Now, how exactly does that happen?
I don't know, Abe.
You might be wondering.
I am wondering.
If we look at the laws of physics, let's take a simple example. Say you have a pendulum that's going back and forth, and you're watching the video. And then I hit the reverse button. Now you're watching it going in reverse. You can't tell whether this video is being played forward or backwards. The same thing with any simple system. Have you ever played the game Pong?
Like the old, first video game ever, Pong?
Exactly.
With the 2 bars and the ball.
Exactly.
Yeah.
If you've ever seen a game of Pong and then you played it backwards, you cannot tell whether this is being played forwards or backwards. A game of Pong cannot be distinguished between forwards and backwards, between past and future.
What if I lose a point? Does that mean?
Before you lose the point.
Okay.
We should restrict it. Now, the interesting thing is, the laws of physics don't care whether you're going forward or backwards in time. You can replace all your equations with a minus t or something, and then the universe would not care. However, there is this one law that is not symmetric with respect to time, with respect to future and past. And that's exactly
The law of entropy.
the law of entropy.
Of course it is.
Because we know that entropy increases, then we can define the direction of time as the direction of which entropy is increasing. Now, a quick side note, there are some other phenomena that happen in the subatomic world that seem to be also violating this past-future distinction. So if you play them backwards on a video, you would be able to tell that okay, these things are going backwards. And so it's not just the second law of thermodynamics that violates the so-called T-symmetry, time symmetry, as in you can play a video forwards and backwards and it wouldn't make a difference. So we know entropy does not obey that law. And there are other, be it very small phenomena that do this, but the big one that physicists are concerned with is entropy. And that's because we know that entropy always increases, and therefore you could define a direction of time to be when entropy is increasing.
So the only way to reduce entropy is to go back in time.
Exactly. And if take a system where the entropy is not changing, then there is no direction of time. There is no future, there is no past.
Huh.
That's
almost like me. I have no future. That's very interesting.
But you have a past.
We all have a past. A dark past. So that's interesting. That explains why that when you kind of think back to the olden days, why they seem so much simpler and so much better, because the simpler times had less entropy. It was back in time, in a simpler time. While
true poetically
and
physically.
Good enough for me. I'll take it. Stop right there. Quit while you're ahead. It brings up, the ideas of nostalgia, but that's a topic for another day. Abe, do we have any final thoughts on entropy, or would you like to start taking these audience questions that are flooding in?
Questions sound like a great idea, but first, I'd like to talk about Maxwell's demon for a second.
Maxwell's demon.
Yes. Now, we brought up Kelvin, we brought up Clausius, we brought up Boltzmann. You can't talk about entropy without talking about Maxwell.
Oh, of course. Maxwell, who could forget?
Now, Maxwell, if you remember our first episode, was the Maxwell who was able to write down the equations for the electric field and the magnetic field.
Same guy.
The same guy. The fields that govern your everyday life, that keep the world together, this was the guy. He also worked with thermodynamics.
Wow, throwback to our first episode. Things were so much simpler back then. So much less entropy in the universe. Those were good times. So
you just got to deal with the increase in entropy, man.
I can't. It's too much. So Maxwell, he
envisioned this demon who would do the following thing. Imagine you have a box, and then
with a cat in it.
That's Schrodinger.
Oh, okay.
But we could talk about the cat some other time. So with Maxwell, though, you imagine a box. One is filled with very low temperature atoms, something like cooling temperatures. And then at the other side of the box, there's very hot atoms. And then there's sort of a partition between them. And then you remove the partition. You let the gases mix together. All right. What's so fancy about that? Nothing. The gases are going to mix. The entropy is going to go up. All's good, right?
Sure.
And then you place back the partition. You split the box into two. And then Maxwell's demon comes along. And then he knows exactly how each particle is moving, where it's going, what's the mass, the velocity, all of it. So what he does is he opens a little gate every time he sees a fast particle moving. And so he forces it to go to the right end of the box. And every time you see a very slow moving molecule, which means cold, then he opens the box and forces it to go to the left end of the box. And so if you keep doing that, you'll notice that all the cold molecules are going to be on one side of the box, and all the hot molecules are going to be on the other side of the box. And so effectively you have reduced the entropy without putting in too much work.
Well, this seems like there's a lot of work behind this.
That's one of the objections, is that the demon must be doing work, right? I mean, you can't just willy-nilly let particles go here and there. But if you can imagine the gate being very weightless, if you want, such that when you move it, it doesn't take a lot of work to do. You just, you open it and you close it, in a sense, and that doesn't take a lot of effort to do. And so,
but if you have to do it for every single
right,
atom,
you have to do it for all these atoms. But then the question is the total entropy, has the total entropy increased or decreased
within the box?
Within the box, and then you have to consider the demon as part of the system
itself.
Right. And so that was Maxwell's demon, and it's sort of a paradox. How could entropy? Yeah.
See, I feel like there's a lot of contradictions to that, because to have such a system that could open up and close a gate no matter how small or weightless, on such a like how many times it would have to occur consistently, would have to take up energy from somewhere, and that energy would have to be coming from outside the box.
Right, that energy must be provided by the demon. But in Maxwell's case, he was imagining the case where you could make a system such that you don't really need that much energy to split the two gas molecules into hot and cold. All you need to know is the information of each particle. And that's where the idea of information and entropy comes into play. Later on, it was conjured or theorized that actually entropy is a measure of information of a system.
Can you, if entropy exists in the way that you're stating, can you fully understand everything? Can you have information on everything at all times, or is there randomness that's naturally built into the universe?
Now that would take us into quantum mechanics, but classically everything is determined. So given some sort of configuration like you and I right now, we're made up of molecules and we obey the laws of physics, then in theory, in classical physics, every move that we make is determined.
I believe it's referred to,
is stored.
So I believe it's referred to as a Google plex for the number of, it's like 10 to the 100th power, for the number of infinite possibilities to fully grasp every single, down to the molecule in our entire universe, in every possible situation. Yeah, so imagine like you have a box, right? A 3x3 box. There's 9 cubes in it, that area. So imagine every quark being the entire universe, being that small little.
You gotta tell us what a quark is.
A quark is the smallest thing in the world, smaller than an atom. It's down to the basics. Imagine having something that small, but knowing every single position. So like knowing these big cubes that are in the square, knowing every single position that define us, that define our universe. That number, Google Plex, encapsulates every possibility of these quarks to be arranged in. So basically every possibility for the universe to be arranged in, and therefore every possible reality that could exist. All from the simple number called a Google Plex, 10 to the 100. Doesn't seem that big, right? 10 to the 10 to the 10. That's ridiculous.
Yet it carries so much information in it.
So if you were able to know all the information behind these quarks, would that mean entropy, does that mean free will exists?
That's actually, last time when we were talking about free will, I was going to bring this up because some people have linked the entropy to information, and then, well, wait a second, if entropy is going up, then information must be going up. Well, where is all this information coming from? And there are different theories about that.
Free will.
One of them is free will, and then the other one is quantum mechanics, which we might talk about next time.
I'm so glad that every question in the universe can be answered with, just quantum mechanics.
Just quantum it. We quantum everything.
Well, it looks like it's that time, the end of our episode. Thank you again, ladies and gentlemen, for joining us on From Atoms to Axons with
Bilal Hamoud
and Ibrahim Shahrur.
We hope that your mind has reached a lower entropy state with today's information.
And we hope that your life gains entropy as you are always moving forward, just like the progress of time. Can't wait to see you next week. Have a good one.